Welcome back to the Development Lab. The next lecture that we're going to present is on I/O. Now I say lecture, you see me introducing the subject and then I go to the screen. So it's really a screen recording in the software, and this is the sequence that we would do in a live classroom. Once we've gone through RSLogix 5000 or Studio5000 and kind of presented the overall venue and format, then we would create a project, and of course a project needs I/O. So the next subject is adding I/O to our project. So let's do that. In our last video, we were connected to an L31 processor that has two RS-232 ports, no Ethernet. In the manual, I did vary the processor when I was showing the addition of different I/O other than the IQ6XOW4. What I've done here is I'm now connected up to a different processor, and we're in RSLinks. Go here and do an auto configure. Now I'm plugged into the RS-232 port on an L35E. Hit auto configure and it was already set at 38.4. Now there's a reason I'm doing this. You'll see in a minute. So we'll close, minimize RS-232. As long as we're in there, we'll go to RSWho and we'll stretch her out a little bit. We have a different processor. So at first it showed the red X, but now it shows it's there, but it says L35E, and the last time I put a program into that, I called it station test _ L35E. The name is irrelevant. And now we see something slightly different than we had with the L31. Now we see that we're plugged into the RS-232 port, and then we have the processor. We have a Ethernet daughter card that's built into the L35E, and then we got the local bus. If I expand the Ethernet, well, it's really not going to go anywhere because it just shows it itself. It's showing itself. This and this, that card and that card, that's one card. This is the actual card, and this is a placeholder in the display for Ethernet. If we had other things hooked up to that Ethernet, they would show up. Go to the bus adapter, and there's what we had before. We had the IQ6XOW4, and then we had the combo analog card. Both of those cards are there for the L35E. I can also go to the L35E and go to device properties. I can see it's Rev 20.12, and I can see the serial number. A minor recoverable fault, that's probably battery. If I go to the Ethernet port and go module configuration, see general, but port configuration, looky here. We're set for a static IP address with that subnetwork mask. We won't go into a discussion right now on Ethernet and subnet masking. You probably have all set these at one point or other in your career. If I go to dynamic, then I have to choose between DHCP, which this processor then on a server would acquire its IP address leased to it for whatever the network manager allows. Boot P, you would have to have a Boot P server, and a Boot P server would always give it the same IP address. Boot P is kind of like DHCP Rockwell Automation style, Rockwell software style. But no, we want static. And just for grins, I was going to reassign this, but I think first, this is all good. I'm going to go to my computer. I'll go to control panel, thinking, network and internet, network and sharing center, go to change adapter settings, and right now there's my wireless. And this is my local area connection. So I'm going to right click, properties. We're using, and we're set at 192.168.122. That's the IP address that my laptop is set at. Because the subnet mask is 255.255.255.0, which would really be 81s, 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 and then the last 8 ones or ones and zeros, in other words, the last 0 through 255, that would have to match. So my laptop's at 22 on that subnet. This subnet, 255.255.255, that's not the subnet. That's the subnet mask. This is the subnet, 192.168.1. That's my subnet. My laptop is 222 on there. I just want to double check that. So now, see, this is the same subnet, and my processor is at 111. So I didn't change anything, but I'll hit apply and OK anyway. Now, I could have changed it at that point. I could have changed the IP setting for that Ethernet processor right there in RSLogix. That's the best way to change it. However, instead, I'm going to open up RSLogix 5000. Notice it shows all the versions that I have loaded, 17, 18, 19, and 20. I don't care about the start page, so I'm going to close that. I'm going to go to Communications, Who Active, and see who I find. Well, I found the L35E. Now, I'm going to say go online, but I would be surprised if it went online without a hiccup, because remember, it goes to the L35E, gets information, then comes back and compares it and says, hey, I don't have an offline project that matches the name of the project that's in the L35E. Well, looky there. It looks like it might have found one. We'll see. See the blue up here? Remote program mode. Now, it didn't find one, so it's wanting me to select a file. So instead, I'm going to cancel. I'm going to go create a file. Okay, File, New. Our controller is an L35E, version 20. Called it Beginner L35E IO. Just like that, and PLC Professor 5000, Learn 5000, RS5K Beginner Recording. Okay, there we have it, an L35E, revision 20. We named it, and we're saying to save it in that special folder that we created. Okay, here's our L35E project. We know what our IP address is, 192.168.1. That's our subnet work. And then the laptop is 222, and I think the processor was 111. We created this L35E because we wanted to show you two things. One was some different I/O configurations, and the other was Ethernet configuration for RSLogix. So if I go to RSLogix, and it's also down here in System Tray, but go to RSWho, we have DF1. We don't have Ethernet. If I want to do an Ethernet driver, in other words, I want to use Ethernet, I have to go to Configure Drivers, and I can pick either one of these two. I'm going to pick Ethernet devices because it's more deterministic, meaning that you have a little bit, you can see where you're going with it, where this, it actually will browse the subnetwork and find the devices. But we're going to go to Ethernet devices, add new. I'll leave the default name, and then the first one I'm going to put in is 192.168.1.222, which is my laptop. Then I'm going to add 192.168.1.111. That's the processor. I'm going to hit apply. In other words, I had to type in all the IP addresses that I want that driver to find. So I close that. Then I go to RSWho, and I expand the Ethernet, and look what it finds. It finds the processor on my subnetwork at location 111, and it finds my laptop, RSLogix, at 222. That means I configured my Ethernet driver and it works. To further prove that, I can expand, and I'm going to stretch this out because this is a good opportunity to make a point. There's my two modules, my IQ6OW4 and my IF4XOF2, my combo digital card and combo analog card. These are typically my standard cards for training development because you can do a little bit of everything. Now this is the Ethernet. So I'm going to drag this up, drag this down, and we'll let that fill up the whole thing. So now I'm going to open up this driver. Do you see any similarity there? Remember, there are two ports on the front of this processor. The highest one is, physically, the top one is Ethernet, and the bottom one is RS-232. If we look at the entry point for DF1, the RS-232, it shows the processor, and it's going in this bottom port down here. If we show the Ethernet driver, it shows it going in the daughter card, which is that port right there. It doesn't show a picture of the processor. It shows the daughter card. Then it shows it plugged into the backplane, and in the backplane is the processor. Now this is the processor right there, and you can tell by right click, you can do device properties and see something. If I were to right click on this, see, that's the entry point. This is the entry point. If I right click, module configuration, this isn't the processor, and there's my Ethernet setup, which I can access from here. The point where you lose identical tree structure is right here. Local 1769, local 1769. Next up is Ethernet card. Next up is the processor. And it's all in relation to the backplane. The port on the front, right there, the Ethernet port or the RS-232 port, goes to the controller and to the backplane. And then on the backplane we have all these other things. So right now we are communicating with RSU to the processor and the backplane through RS-232. If I click here, now we're browsing the Ethernet. Right now I'm showing you both ports on that L35E can communicate, which means you can have two different things going on, one through the channel 0 and one through channel 1. Now on the L31, they're both RS-232, channel 0, channel 1. The L35E, channel 0 is one protocol and channel 1 is a different protocol. Okay, that's enough for that. Now here's what I wanted to show you. I'm going to add different I/O and not use what we were using with the IQ6OW4. It would really behoove you to have a 1769 IQ6XOW4, but if you don't, then here's something you might have. Go to Compactbus local, new module. I typically put input modules first, then output. I guess because in the program scan, it does inputs, does the program, then does the outputs. So I think of the inputs as always coming first. It really doesn't matter. I'm going to type in IQ, and I'm going to pick an IQ16. I'll just pick I don't really know which one I have. Let me go look in RSLogix real quick, because this is a different chassis that I grabbed with an L35 on it. So I'm going to go RSWho. We can go Ethernet or RS-232, but remember that Ethernet is always quicker. Oh, that's also got a combo module. So I didn't grab one that had an IQ16 and an OB16. So we're still working with an IQ6OW4X, except that's not what I wanted to show you. I took advantage of the L35E that I have immediate access to. I'm going to go ahead and add I/O cards to it that aren't actually the I/O cards on the chassis. We're going to do this offline. Whether we do it offline and then download it or not download it, just show you how to do it, it's going to work out the same. So we go to Compactbus local, new module, and I'm just going to type in an IQ. I'm going to pick an IQ 16 because you're more likely to have the less expensive of the two modules. We'll just call it DC inputs, and it's in slot 1. That's how I usually name my stuff. And I'm not going to change the series or revision because I don't really have this card actually in front of me right now. Okay, so there's an IQ 16. Go through that process again and pick an OW or OB. If I went OW, then you see there's my combo module. Or you can see that I have an 8 relay out, 16 relay out, or 8 isolated out. It's more likely that you're going to have an OW16 than an OB. See if I went back and changed that W to a B. An OB16, that's a DC output card instead of a relay output card. So we'll just assume that you're going to have an OW, and we'll call this relay outputs, and it's in slot 2. And again, we're not going to change the series of the revision because we don't really have this card. I'm just showing you how to add these cards. Now that these cards are added, we can open up the controller tags, and see we have only one data type for the IQ16, and we have 3 data types just for that one output card. If I go over to here and go to module defined, you see there's one digital input, 16. So that tag right there, that class of data objects, has an instance called local:(I:1). When you expand it out, it has 16 data bits, and then it has some fault for a fault code. Whereas the relay output card, there's its 16 outputs right there. Those are the memory locations for the 16 outputs. You also have inputs. You have read back and fault. We're not going to look at those. You also have configuration, and that's configuring what you want that module to do if the processor faults, and what to do when you go into the program mode. We're not going to cover that right now. I just wanted to show you what they look like. These 2 sets of tags right here, data, those 16 bits are your outputs. These 16 bits are your inputs. We can't get them all on one screen capture here. But those would be the 16 bits for inputs, 16 bits for outputs. That's an L35E, and we actually looked at that online, and we configured the Ethernet driver and discussed it. Now let's go another I/O possibility. And to do that, I'm going to delete both of these I/O cards, and I'm going to change the processor to a L23E. So change controller, go to an L23E, not an L24. That's the newer 5370. I mean, we can do that with version 20, but that's not what we're doing. So we want the L23E. That's no E there. See, L23 and L23E. The L23 has 2 RS-232 ports on it, and the L23E has 1 RS-232, 1 Ethernet. We want revision level. We say OK. Changing the controller. This is a generic message. It says, changing it will change, delete, and/or invalidate controller properties, other project data. Change controller type, yes. Still thinking. You can see the cursor flickering. Okay, now look. Remember that we deleted all of the I/O. 2 cards, an input card and an output card. And now look at what we have. We have 4 embedded I/O modules. In other words, they're built right into the controller. And there's a picture of one in your manual, roughly on page 60 or so. It explains what you see here in front of you. For module defined types, These right here are special. See, they say embedded. These do not. So this digital input and this digital output looks exactly like what we saw before with our L35E, our IQ16F, and the OW16, but this would probably be an OB because that's what they're using, is an OB, not a relay. You can tell by color. If you looked at the front of the processor, you see blue, green, then you see a split, brown and yellow, and then you see pink. The blue is input, DC input, the green is DC output. The split, if you want to call it orange and yellow, I call it brown and yellow. One is analog inputs, the other is analog outputs, and then the pink is the high-speed counter module. AB kind of sticks to that color code when identifying their I/O. So here now we have another yet configuration for I/O. So our digital inputs would be these 16 bits right here, local, slot 1, input data, 0 through 16. And if you were using this with this manual, you would be using 0 through 5, just these 6 inputs to do your labs with. Your outputs would be in slot 2 here. There's your 16 outputs. You would be using 0, 1, 2, and 3, just 4. Because remember, our labs are built around 6 in and 4 out. And you have to be able to correlate going forward your tags for your module defined tags, your instances, against what's in the manual. Because in the manual, we're going to have local 1I data and local 1O data, not 2. Because this is 2 separate modules. The next thing that we did in the manual was RSLogix. Although Compactbus is the most popular for learning simply because it's less expensive, RSLogix has a popularity because of its versatility. You can do a lot more with RSLogix than you can Compactbus. However, most of that can do more, covers areas that you don't need for most projects where you use a programmable automation controller. Let's bring up our project. This was the controller was an L23E QBFC1. Actually is more to the part number than that if you have embedded analog and high-speed counter. So we're going to close this project. We don't care whether or not we save the changes because this is not a project we're going to use. I'm just showing you some procedure. Let's create a new project, only we're going to pick we'll just take an L71, we'll make it version 20, and we'll call it RSLogix L71. I might have had you name it something different. It really doesn't matter what you name it. We just need a processor, and we're going to save it in that same spot. Okay, in the background, the Rockwell software geeks are creating this data structure with all these containers, and there you have it. Notice that with the RSLogix, you've got even less shown for the I/O configuration. However, it did show a 1756 A10. That means a 10-slot chassis. And I failed to mention, when you created the project and picked your controller, you can also pick a chassis, 7, 10, 13, 17, or even this 5-slot here. We'll make it a 7, even though it started with a 10. We'll say apply. Really doesn't matter because we're not going to fill it up. But notice that the controller is shown in slot 0. Let's change that. Let's go to controller properties. This is the controller. I'm going to put it in slot 5. Okay. Now see, it says 5 here. And if I wanted to, I could put another controller in this chassis. But let me point out something very important. When you're working in a project, you are working in a project for a controller. within a project, you cannot write programs for two controllers, but you might include another controller in your project, actually shown on the backplane for certain other reasons, producer consumer, that we're not going to discuss at this level for the beginner lab project manual. But I put it in slot 5 just to make a point. Now I'm going to go to the backplane and I'm going to add a module, and I'm going to add an IB. See, if I typed in IQ, there are no IQ modules because this is 1756 IO, not 1769. I can go IB and pick an IB16 diagnostic. That would be the expensive one. An IB16D, that's got all the bells and whistles. So we'll pick that. I double clicked on it. We're not actually working with this hardware, so it doesn't matter what the revision level is because we're not going to download this anyway. This is an IB16D, so it's DC inputs. We can put it in any slot we want. Just for grins, I'm going to put it in slot 3. Typing in 3 here doesn't put it in slot 3. Over here is where you put it in the slot. As a matter of fact, I'm going to put it in slot 0 just to make a point. Remember that this name is arbitrary, so you typing in a number here doesn't configure or assign anything. But I'm going to put it in slot 0 because that's the most unusual place to put it. And I'm going to disable keying, say OK. Now you see there's an IB16D in slot 0, the processor's in slot 5. I'm going to talk about a few things real quick. This was the general information. We just put that in there. This is the connection. And in the connection, we have something called a requested packet interval. To explain the requested packet interval, we're going to have to back up. Some of this was discussed in the lab project manual. Some of it is discussed in other lectures. But what sets ControlLogix apart from Compact or FlexLogix or any of the other Logix engine platforms is that the backplane for ControlLogix, the 1756 chassis, are a passive backplane. That means the backplane is not actively involved in the I/O updating or communications. You need to think of the backplane on a 1756 chassis as a 32-bit parallel network instead of a serial network like Ethernet or RS-232. Well, RS-232 is not a network, but it's serial. Means you have one line level that goes up and down at a baud rate to communicate. So you only communicate one bit at a time. Ethernet, device net, control net, whatever. It's one bit at a time. It's serial. The backplane of a 1756 chassis is a 32-bit parallel network. And everything that plugs in to a 1756 backplane is capable of communicating on the backplane. Any of the MicroLogix products or SLC500 or PLC5, those are active backplane, meaning that the control of the backplane, it's an active process to collect inputs and hand out output states to the output modules. The controller actively controls the backplane for MicroLogix, SLC500, PLC5. With ControlLogix, the processor does not control the backplane. It is simply an entity to communicate across the backplane. Now the processor is going to run the show, but the reason you have an RPI with this input card is, if I leave it set at 20 milliseconds, what this says is this card, this module, is configured to update the processor's I/O image every 20 milliseconds. With this configuration, when this processor over here under I/O configuration, when it goes into the run mode, as it's going into the run mode, it's going to go out and find everybody in its I/O configuration. Right now there's only one, that IB16D in slot 0. It's going to send a message out to slot 0 saying, are you an IB16D major rev, minor rev, series, blah, blah, blah. And then the IB16 receives that communication, receives that message, and then it replies, yes, I am. Then the controller, at that point, has established a connection with that module. The next thing is the processor is going to say, all right, IB16D in slot 0, you belong to me. And here's what I want you to do. Every 20 milliseconds, I want you to send the state of your inputs over the backplane to these memory locations. What this means is, with RSLogix, that its continuous task is more continuous in that it doesn't have to stop executing the program and run a process of collecting the states of inputs from different modules. Those modules report in on their own at their RPI, the requested packet interval. Now there's a lot more to 1756 I/O than what we're explaining right here. I'm going to show you just a few things, but I'm not going to go into a lot of detail. First of all, of course, there's no module info because there's no module. Yet you'd have to be online to see anything here. Configuration, this is really cool, but they don't give away these modules for free, meaning these extra features are nice, but you do pay for them. One is that you can enable change of state. Remember, we have a connection, and when it says connection, it literally means a communications connection, established connection. It's set at 20 milliseconds. So every 20 milliseconds, this module will send a message to the processor, to its memory location, with the state of the 16 inputs. And for any of these that are checked, we'll uncheck them all. And let's just check this one and that one for our explanation. And if point 0, input point 0, goes from off to on, immediately update the I/O image in the processor's memory. However, if it's going to update 0, it's going to update all 32 bits, whether it's 16 or 32-bit card. So when you have change of state enabled, it updates all the I/O if any of the ones that you have selected for change of state actually change state. I'm only updating the input image if bit 0, input 0, goes from off to on. When it goes back to off, I don't update the memory. However, for input 4, we want a change of state from on to off. If that occurs for input 4, then update memory right now. It's going to update the I/O data table, the memory, the part of memory in the processor for I/O, every 20 milliseconds no matter what, and anytime either one of these two conditions occur. So if you leave these all on, it may not hurt anything, but it's going to cause extra activity on the backplane and eat up bandwidth. I wouldn't leave them all on. Matter of fact, I would turn them all off to save a little bandwidth. Also, it's going to do open wire diagnostics. Open wire means that if the field wiring has a break in it or it's open, then it's going to state that there's an open wire condition. I uncheck these and I only check them for solid state field devices, because solid state field devices, they have leakage current. Whether they're off or on, there's current in the field wiring. That's what this can detect. Let's say you have a photo eye and it's hooked to input 1 here. It's solid state, which means, and this is a solid state input card, meaning that it has an opto-isolator. Whether that photo eye is in one state or the other, there's always going to be some current flow. If that current flow goes to 0, then that means you have a broken wire or the photo eye has been disconnected. And you can latch in. If I only had one of these, I would probably only check that. If that condition occurs, I latch it in. If I'm looking for an intermittent connection, I can find it. This is basically a debalance timer. You have 0, 1, or 2 milliseconds. By default, it's set at 1. Input 0 through 7 is set for a 1 millisecond off to on and 1 millisecond on to off, let's say delay. If any of these inputs right here, 0 through 15, if they change state, but they only change state for 1/2 of a millisecond, 500 microseconds, the state of the inputs won't change. In other words, it ignores these little noisy spikes. In groups of 8, you can set these debalance, if you want to call them that, filters 0, 1, or 2 milliseconds. And then, of course, if you want to reset a latched diagnostics, you do it right here. You just hit that button. Now, you'd have to be online to do this. You could go reset that latch, and you can do that from your code. These are all addressable in the data table. So we'll hit apply, and let's go add an output card. New module, we'll make it an OB16, 16D. That's the diagnostic, that's the expensive card. Got all the bells and whistles. So we'll do DC output, and just for grins, we'll put it in, see, we have a 7-slot chassis, so we can put it in 6. That's the last slot of a 7. Let's go to configuration. The RPI is the same thing. Now, you're saying, well, hold on now. Why would an output card need an RPI? Because output cards receive information to control outputs from the controller, not like an input card. However, all of these cards are smart. They all have RISC processors, they all have firmware, and they all have memory. Go to configuration, we can pick what we want each output to do if it goes into if the controller goes into the program mode or the fault mode. We can select whether we want it to go on, off, or hold the last state. We can verify that the output came on. There's more to that than what you think. Verifying the output means that in your program it's said to turn on output, in this case we'll say output 1. That then, through the opto-isolator, turns on or energizes the field device, which means the current level in the field side of the wiring, not the module side, but the field side of the wiring is going to see a change in level. If you turn on output 1 and the card, the module, by monitoring the current, a current sensor in the field wiring, if it doesn't see an increase in current, it's going to say the output didn't come on. This isn't really necessary for most projects, but if you have real critical outputs, it could be. Also, it's going to detect no load. So again, if you have a solid state device and you have a off state and a non-state current, the off state is going to be very low, but it's still detectable. This can tell you that there's no load. There's nothing connected to it. Of course, this is your enable latch for either one of these conditions. And then here's an electronic fuse. Because you're detecting the field side, the current in the field side, if it becomes excessive, it just turns it off. Meaning if your solenoid valve, the solenoid is shorted, it's going to draw too much current. The electronics in the module sees that and sets the electronic fuse, so to speak. In other words, it sets it as open. It's just switching that turns off the output. And of course, here's where we can reset it. The fuse or any of these latch diagnostics. One more quickie here. Sometimes you want to test to see if you actually have a connection. If you were online and you had these going to solenoids for a valve body, by clicking on test, it sends out a really quick little pulse, not enough to turn it on, just enough for the entire output circuit to go up to some value and back. And because you can detect current in the field side, it can tell you whether or not you actually have a connection out there. Okay, that was a mouthful. So there you have it. And here's your controller tags. This would be for your inputs. There's your, well, 32 bits. Even though it's a 16-bit card, it still uses a double integer. 0 through 15 are your actual inputs. 16 through 31 are just hanging out in the breeze. They don't do anything. And then for your outputs, there's your output data right there. Again, it's a 16-bit output card, so 0 through 15 are those are your output addresses right there. 16 through 31, they're just hanging in the breeze. Everything in RSLogix is native is DINT, double integers. So there you have it for RSLogix.